Dear students, welcome to the next lecture of Inorganic Chemistry. In this lecture, we shall discuss about the oxides, oxoacids and peroxoacids of group 16 elements. Sulfur, selenium, tellurium and polonium forms different oxides. The oxides of sulfur are S2O, SO, SO2, SO3, S2O7, etc. There are several unstable oxides of sulfur such as S2O2, S2O3, S7O, S8O, etc. Selenium forms SeO2 and SeO3. Tellurium also forms dioxide and trioxide. Polonium forms mono and dioxides. Let us discuss about the structure of sulfur dioxide and sulfur trioxide. SO2 is an angular molecule with bond angle 119.5. The both SO bond lengths are same, 143 picometer. The structure of sulfur dioxide can be explained on the basis of VSEPR theory. The ground state electronic configuration of sulfur is 1s2, 2s2, 2p6, 3s2, 3p4. In excited state, one of the electrons in the 3p orbital gets excited to the vacant 3d orbital, and sulfur undergoes sp2 hybridization to form 3 hybridized orbitals. And out of these 3 hybridized orbitals, one of the orbitals contain the lone pair of electrons. The other 2 hybridized orbitals form sigma bonds with oxygen atoms. The electronic configuration of oxygen is 1s2, 2s2, 2p4. Each oxygen atom forms one sigma bond with a sulfur atom. And the third sp2 hybridized orbital contains the lone pair. These 3 hybridized orbitals are arranged in trigonal planar fashion, and the bond angle is slightly less than 120 degree, that is 119.5. This can be attributed to the fact that lone pair bond pair repulsion is greater than that of bond pair repulsion. There are 2 unhybridized orbitals of sulfur containing 1 electron each. One 3p unhybridized orbital and one 3d unhybridized orbital. The 3p unhybridized orbital forms pi bond with the 2p orbital of 1 oxygen, and this bond is called p-pi bond. The 3d unhybridized orbital containing 1 electron overlaps with the p orbital of the other oxygen to form d-pi-p-pi bond. In the resonance structure, the d-pi-p-pi and p-pi-p-pi bonds are interchanged. Resonance structure of sulfur dioxide can also be represented like this. Next is sulfur trioxide. In sulfur trioxide, the excited state of sulfur has the electronic configuration of 3s1, 3p3 and 3d2. That is, one 3p electron and one 3s electron are excited to the vacant d orbitals. And sulfur undergoes sp2 hybridization to form 3 hybrid orbitals with 3 unpaired electrons and 3 unhybridized orbitals with 1 electrons each. And the hybrid orbitals, sp2 hybridized orbitals of sulfur overlaps with oxygen to form the sigma bonds. So each hybridized orbital containing 1 electron overlaps with the 2p orbital of oxygen containing 1 electron and forms sigma bonds. These bonds are arranged in trigonal planar fashion with a bond angle of 120 degree. And the one unhybridized p orbital and two unhybridized d orbitals containing 1 electron each overlaps with the p orbitals of 3 oxygens to form p pi p pi and d pi p pi bonds. In SO2 there are 2 d pi p pi bonds and 1 p pi p pi bond. The resonance structures are shown in the figure. Sulfur trioxide exists as a trimer S3O9. It is cyclic in nature as represented in the figure. The next topic is oxoacids of sulfur. First comes sulfurous acid H2SO3. An aqueous solution of SO2 is generally called sulfurous acid. But sulfurous acid has never been isolated. Some species like SO2 NH2O, which is the hydrate of SO2, are isolated, and the hypothetical structure of sulfurous acid is shown here. Sulfur is bonded to an oxygen by a double bond and two OH groups by single bonds. Sulfuric acid is H2SO4. It is otherwise known as tetraoxosulfuric acid. There are two ionizable hydrogens, and thus sulfuric acid is dibasic acid. In aqueous solution, it decomposes to HSO4 minus, and HSO4 minus further decomposes to SO4 2 minus anion. Sulfur is bonded to two oxygens by double bonds and two OH groups by single bonds. The molecule has a tetrahedral structure. Disulfuric acid is H2S2O7. It is otherwise known as fuming sulfuric acid or oleum. The structure of disulfuric acid is shown here. It is also called pyrosulfuric acid. H2SO4 plus SO3 gives H2S2O7. In pyrosulfuric acid, there is a sulfur-oxygen-sulfur linkage. That is a bridging oxygen atom, and each sulfur atoms are bonded to two oxygen atoms by double bonds and one OH group by single bonds. Next is thiosulfuric acid, H2S2O3. When one oxygen of sulfuric acid is substituted by a sulfur atom, we get thiosulfuric acid. The molecule has a tetrahedral structure with sulfur as the central atom, bonded to two OH groups by single bonds, one oxygen atom by double bond, and there is a S double bond S present in the molecule, and thus it is called thiosulfuric acid. It is formed when SO3 reacts with H2S. Another class of acids of sulfur is peroxoacids. There are two peroxoacids, Caro's acid and Marshall's acid. In peroxoacids, there is a O single bond O, that is peroxide linkage. Caro's acid is H2SO5. It is formed when H2O2 reacts with HSO3Cl. In Caro's acid, the sulfur atom is bonded to two oxygen atoms by double bonds, one OH group by single bond, and there is a sulfur oxygen single bond, and that oxygen is bonded to another OH group. Next is peroxo disulfuric acid or Marshall's acid, H2S2O8. It is prepared when H2O2 reacts with two molecules of HSO3Cl and H2S2O8 in aqueous solution exists as an equilibrium of sulfuric acid and Caro's acid. The equation is H2S2O8 plus H2O giving H2SO5 plus H2SO4. In Marshall's acid, there is a peroxo linkage and each oxygens are bonded to sulfur. The sulfur atoms are bonded to two oxygen atoms by double bonds and one OH group by single bond. Next is oxoacids containing sulfur-sulfur linkages. Dithionous acid is an example for oxoacid with SS linkage. Dithionous acid is H2S2O4 there is a sulfur-sulfur linkage, and each sulfur atom is bonded to an oxygen atom by a double bond and OH group by single bond. Dithionic acid is H2S2O6. There is a central SS linkage, and each sulfur atom is bonded to two oxygens by double bonds and one OH group. Several polythionic acids are also known. An example is H2S5O6. The structure of H2S5O6 is represented here. And polythionic acids are not so stable. They decompose into sulfur, SO2, SO4, 2-, etc. But the anions of polythionic acids are found to be stable than the acids.